The next talk is a contributed one, and the title is Improving Semantic Parsing for Task-Oriented Dialogue, and it will be presented by Mrinal Mohit.
Thank you, Dialog. Hi, I'm Mrinal Mohit. I'm a research scientist at Facebook Conversational AI. And today I'll be talking about improving semantic parsing for task-oriented dialogue. So before I can talk about improving X, I'll need to talk about what X is. So most modern task-oriented dialogue systems are usually implemented as a pipeline. Say the user asks, how's the weather tomorrow? A natural language understanding engine figures out that the user wants to know the weather tomorrow. The dialogue policy knows that it needs to ask the user for the location of the weather call, and then the user provides Montreal, and that is executed, and a natural language generation system responds to the user in the proper language. Now, the way so we'll be talking about the NLU subsystem in this talk. The way most traditional NLU systems work is that, let's say you have an utterance like, how's the weather tomorrow in Montreal? The NLU system will first mark the entire sentence as, say, intent get weather, which is a document classification task, and mark Montreal as a location slot, which is a word tagging task. And this translates very well into something like an API call, where the method is get weather and the slot is Montreal. And this has been very well studied and is implemented in most production systems out there right now. The problem is that it's limited. If you consider something like turn off the lights and play music, now suddenly you want to perform two actions in one request, which does not bode well with our framework of having one intent per utterance. Or if you have something like how far is the coffee shop, you probably want to figure out which coffee shop the user is referring to and then get the distance. So there are, in some senses, two API calls involved. And of course, the classic case of saying text Anusha, the song I was just listening to, there's no way a current system will figure out the song you were just listening to. It will probably take it as verbatim. And this all suggests that we probably need some sort of compositionality in our systems. And that's what we introduced in a paper earlier this year at EMNLP, where we introduced the task-oriented parsing representation. So for one of the utterances in the previous slide, how far is the coffee shop? Now, instead of just marking an intent and a slot, we predict an entire parse tree. And in this parse tree, we know that the get distance intent is a top-level intent, which expects a destination slot, but the destination slot is itself resolved using another API call to get restaurant location with type food as coffee. And the advantage of this is that this is much more expressive than the traditional representation, but much easier to annotate than full logical forms like graph structures. And that means you can actually go ahead and annotate a lot of data and put this into production. And this can easily be integrated in existing execution engines because you can make an API call like get restaurant location, you get a result back from that, and that just feeds into the get distance call. Another advantage of the stop representation is that you can use standard tree parsing techniques. For example, we use the recurrent neural network grammar introduced a couple of years ago by Chris Dyer's group, where we have 3 stacked LSTMs. And the embeddings of these stacked LSTMs feed into an action classifier, which predicts the next action to take while constructing the tree. So let's go through an example. Let's say you have how far is the coffee shop as the utterance. You feed that into the buffer stack LSTM, and the first action which pops out is get distance. And get distance goes into the stack and the action LSTMs, but also the action LSTM corresponds to forming a tree. So let's say the next action is shift, which means take something from the buffer, put that into stack. So you get how far is, and then you open another non-terminal node in the tree called slot destination. Then you keep going on, And at some point, you will want to close out these subtrees. So when you hit a reduce method, you finalize a subtree, in this case, the slot type food subtree, and modify your stack so that you now have a composition, you have a representation of that subtree instead of all the elements in the subtree. So we finalize type food. Then once the buffer is empty, all you can do is reduce and finalize the rest of the subtrees. So keep going on, and ultimately you have a full parse tree. Now the key thing to note is that there is a one-to-one correspondence between the action list and the parse tree. So you can just serialize the parse tree, and that would be your action list. So all of this work was in our previous paper at EMNLP earlier this year. The contributions of the paper I'm talking about today is that we improved the model by doing ensembling. And it's not very straightforward how to do ensembling in such a scenario because you want valid tree outputs. We also explore contextualized word embeddings like Elmo. We also explore re-ranking based on a language model. Once we've tried all these methods, we define the classes of errors for which these parsers exhibit, and then show that these three methods collect different classes of errors, which means that we can probably combine them all together and achieve a state-of-the-art result. So let's go through the first method. We try out ensembling. What is ensembling? We have trained multiple parsers, and the outputs of these parsers might vary slightly. And those sources of diversity could be shuffling the sentences, the seeds of dropout, parameter initialization, a bunch of different things. What we want to do is to combine the output of these three parsers, or n parsers in general, and predict a valid tree output. Now, there are multiple ways you can do this. For example, let's say parser 1 and parser 2 predict the same thing, and parser 3 predicts something else. Here, the closing brackets represent the reduce operation. So in this case, it's pretty straightforward. You just take the majority, and you discard parser 3's output, and parser 1 and 2 give you a good result. If you have something like this, in which parser 1, 2, and 3 all have different outputs, but clearly parser 1 and parser 2 are onto something. They have INA, SLB, and INC as common, and only differ on SLD and SLE. Now, if you use majority voting here, none of them have a majority, so you'll get 1 in 3 chance of picking any of these parsers. What we want to do is somehow bias it towards parser 1 or parser 2. So we do a greedy action approach, in which we first look at the first action. That is common. We go on to the next action. That is common. We go on to the next action, and we realize that parser 3 is no longer in the majority, so we drop that. And when we analyze the next action, we see that both the parsers had different outputs, so we just randomly pick one of those two. But this is still better than the 33% probability of picking them with majority voting. The third approach we tried is something called parser switch, which was introduced a while ago for natural language processing tasks. What the basic idea is that we want to find one parser which has the maximum overlap with other parsers. So this is the same example as the greedy action example, but our approach of computing which parser to choose is different. We compute a constituent set, which basically means that we compute a representation of subtrees for each parser. So parser 1 had 4 subtrees, and that's the label, starting index, and ending index in terms of tokens. Same as parser 2, but with a different slot, and parser 3 has a different subtree set. For parser 1, we look at how many of its constituents overlap with the constituents of the other parsers. So in this case, in the light blue, you see 5 other constituent sets being in common with parser 1, so the score of parser 1 is 5. Parser 2 is also 5, but parser 3 is 4 because now the 2 subtrees which were predicted later do not match. So how well does this perform? In the earlier paper, we released a data set with around 45,000 utterances and corresponding top representations. The base model there had an exact match accuracy of around 80%. This means that 80% of the time, the goal and the predicted trees match exactly. So we see that greedy action and majority voting perform almost similarly. The difference between them could be a little bit of noise, while parser switch is clearly not as good as the simpler approach. We also report the score of an Oracle ensemble parser, which always picks the correct parser whenever possible, so it cheats. But this is the upper bound for ensembling gains, and we see that there is still a difference of around 7 points between our best ensembling strategy and the Oracle parser, which means that there might still be some room for improving our methods. The next thing we tried was contextualized embeddings, also known as ELMO or BERT in the recent work, and I'm sure I don't need to explain to this crowd what those are. But there are different ways you could use deep contextualized word embeddings, and here are the things we tried. We noticed that the first layer, just using the first layer, gives a much better result than just using the last layer. And it doesn't really matter how you combine the different layers. We tried average, learned weighted average, concatenated, as long as you have the first layer in the mix. And a justification for the first layer's better performance on our task can be that the parser needs to identify syntactic properties, for example, opening a non-terminal right after a preposition to produce correct parsers. The third thing we tried was beam search at inference. So we had tried this earlier in our earlier paper. We explored beam search for inference so that the parser outputs n best trees instead of just outputting one tree. And the black bars here also represent the oracle. That is, if the algorithm knew which one of those n outputted trees was correct, it could achieve 90-93% accuracy. This also suggests that re-ranking the top hypothesis can be an effective way of increasing the accuracy. So now you have n outputs. How do you re-rank them to produce a better output? You could do language model-based re-ranking. We take a parse tree, we serialize that, and we train a language model out of that. So for example, concepts by Kendrick Lamar, we serialize that into something which looks very similar to our action list earlier, and O and C here stand for open and close brackets, and we train a language model with that. So what we notice is that if we just use this LM score as to re-rank our n best trees, we get around 82.8% exact match accuracy, which is better than our baseline greedy or just picking the top of the beam. What we also tried was training an SVM ranker, which uses LM score and the beam score as features. We could have used just hand-tuned weights, but this allows us to later add more features easily, which we explore in a later slide. The SVM ranker results in a substantial gain over the top one beam, but there's still a huge difference compared to the Oracle top 5 beam. This suggests that more effective re-ranking approaches, such as including more features, could be worth trying here. So we tried all these different methods, and we still, were not satisfied. We were like, what are the types of errors are the algorithms making? So we went deep into that and looked at the different kinds of errors and tried to taxonomize them. So if you have an example like tomorrow's live events in New York with the corresponding parse tree here, there are different kinds of errors you could get in such a parse tree. And most of them can actually happen both in traditional and hierarchical representations, but some of them are more relevant to our discussion. For example, you could get the top intent wrong. You can have create event instead of get event. And this is an interesting task here because the top intent is the first thing the algorithm predicts. So it doesn't really have that much syntactic information from the rest of the sentence, and it's more of a semantic task based on just the buffer you have. You could get one of the non-top intents or one of the slots wrong, in which this is labeled as slot contact. You could get extra intents and slots where there should not be any. For example, it for the reason detected that New York is a type of food, and you should get the location of a restaurant which serves New York. You could miss this man. For example, here we don't have a slot location, and New York is a direct child of a create event. You could have a wrong split. You could not realize that New York is one entity and split them across slots. And you could have a bad boundary in which you can have other stuff coming into a slot. And finally, you can have wrong join, where things which should be two different slots are joined into one slot. So for example, tomorrow and live is joined to tomorrow's live. So then we looked at, okay, we have these 7 different kinds of errors. We have 3 different kinds of improvements to our model. How do they match up? And we noticed that there are a few things we noticed. The numbers here are the absolute number of errors the base model makes and the relative change for each of the methods. So we see that Elmo is effective across all types of errors, not very surprising. We see that ensembling is much more effective at semantic tasks like top intent classification, whereas Elmo is probably the only method here effective against missing span and wrong join, which are mostly syntactic tasks. Now, this also suggests that combining the methods can be effective in mitigating different types of errors together. So that's what we did. So we have the baseline of around 80.86. I showed you the 3 results we got from individually applying the 3 methods. The next thing we did was ensembling plus LM re-ranking. We took the n-best output from the beam search. We used the LM to re-rank it, and we used those different parsers in an ensemble, and that improved accuracy by a bit. Ensemble plus Elmo gives a significant boost. LM re-ranking plus Elmo gives a boost. And if you combine all 3 together, that gives even more boost. Another thing we tried here was adding another feature to our SVM, where apart from the LM score and the beam score, it also takes into account the number of times a particular hypothesis has appeared in the n-best of the different parsers. And that improves the score finally to 87.25, and ultimately we get around 30% error reduction over the state of the art. So in conclusion, we improved the model introduced in our earlier work with ensembling, with valid tree outputs, importantly, contextualized word embeddings, re-ranking based on a language model. We defined the different classes of errors for the top task, task-oriented parsing task, and show that the methods correct different classes of errors, combine them all into one model. And if you enjoyed this talk, you should come talk to us.
Questions? I think we have time for 1 or 2 questions. Nobody? Okay. Oh.
Hi. Okay. Hi. I was wondering if you had also performed some cross-validation and had some variance scores on your model.
We did have a validation set, and all these numbers were finally performed on a test set, but I don't think we have confidence scores or bounds on our numbers yet.
Okay. Thank you.
I have one question which is related to robustness. So do you have any errors like pronunciation or spelling errors or ASR type of errors in your data set, and do you know how it impacts these results?
So this data set was generated by people typing text directly. So we don't have audio data for this data set. So this data set is clean in some senses, but as we do more work on directly transcribed data, we'll have more insight on that.
Let's think. Oh, one more question. I think we have time for that. So.
I was wondering how many of these top-level intents that you had, and if you had any idea of, I guess, do you think it would scale to like thousands of different intents, or yeah, just any comments on that?
So we detailed all the details of the data set in the paper. We had around 30 top-level intents for this task, and I don't think that it'll be too hard to scale up to a lot of intents. It's just a softmax layer at the end, and you can use standard techniques like hierarchical softmax or fine-grained classification if the intent number goes out too big.
Let's thank the speaker again.
Thank you.